Dear students, I have completed the third chapter, that is current electricity. We have discussed so many things related to current electricity like electric current, then EMF, potential difference, resistors, cells, combination of resistors, combination of cells, and then we have discussed Kirchhoff's rules, Wheatstone's network, meter bridge and potentiometer. These many facts are discussed. Now this chapter is actually continuation of the previous chapter, that is electric current. So in the first chapter you have studied about static electricity, that is charges at rest, electrostatics, means the study of charges, study of forces, study of electric potential given by the charge and potential energy of the system of charges. All that comes in chapter 1 and chapter 2 related to electric charges at rest or static electricity. Now in this chapter it is combining the chapter 3, it is continuation of the chapter 3 I can say, because electric current, whenever it flows in a wire or in a coil or in a solenoid, produces magnetic field. Electric current means flow of charges in a particular time interval, and that rate of flow of charge is electric current. Now here in this we study the effect of current, that is magnetism. So that means an electric current flowing in a wire or a conductor or in a coil or in a solenoid, okay, or in a toroid, produces magnetic field in the surrounding space. So electric current or moving charges, because current means flow of charges, so charges also produce magnetic field in the surrounding space, current also. So that means we are studying the effect of charges and electric current by those charges in motion. Okay, so the pioneer or who explained all this for the first time little bit about this beginning, that is Christian Ørsted. The discovery of or explanation is given by Christian Ørsted. So he conducted the experiment connecting a wire to a battery or a cell. Whenever electric current was flowing in the conductor or wire, he used one magnetic needle or compass needle. Like north and south is there for that needle. Whenever you hold it, it will align in the north-south direction. That means it got affected by the magnetic field in the surrounding space. If any magnetic field is there, that will show deflection. That is what a magnetic needle or a compass needle. So he used one compass needle. That is Christian Ørsted used the compass needle and found that there is some deflection whenever that magnetic needle brought near a current carrying conductor. So current carrying conductor means that circuit must be closed and it is connected to a cell or battery, so there will be flow of charges and that constitutes a current in the wire or conductor. When a needle is brought near the conductor, there is some deflection in the needle, and he found that the deflection in the needle is greater when the needle is brought closer and closer or near and near to the conductor. When it is far away, deflection was lesser. When it is near, there is more deflection found in the needle. And also he tried increasing the magnitude of current. When he increases the current in the conductor, there is increase in the deflection or deflection found to be greater. So this point is studied, and then he used this how to detect the magnetic field and how to trace the magnetic field lines. So like electric field lines, there is another idea called magnetic field lines. So the space around the current carrying conductor, there is some magnetic field. The space around the current carrying conductor or surrounding the current carrying conductor, there is some magnetic field. That magnetic field is detected by the magnetic needle or compass needle. So he did the experiment and he found that the needle oriented in tangential direction to the magnetic field. So this is the conductor carrying current, and I have shown here dot and X mark here. I have shown it is I, that is signifying the current or representing the current. So when the current carrying conductor and current is outward, so this current, right hand rule I say, current is normal outward, this I says, and the magnetic field shown by this needle, north is like this, south is like this. Okay, north is along the tangent, and the conventional direction of the magnetic field is a vector quantity, like electric field only. The surrounding any current carrying conductor or surrounding any moving charge, there will be magnetic field. Space around that magnetic field is produced by the magnet, or it may be produced by a current carrying conductor, or it may be produced by the charge in motion. So that magnetic field he determined, and he found that the magnetic field, this needle was showing tangential direction to the path. Okay, tangent to the path, that indicates the direction of the field is this way. Okay, so the magnetic field is direction in a surrounding the conductor is a tangential direction. Like whenever a particle moves in circular path, the velocity direction is along the tangent, we say. Same way, the magnetic field is along the tangential direction. This also he observed. And when the current direction reversed, say this is the current, it is shown here normal outward. Okay, current is normal outward, the field lines are like this. So field we have to show anti-clockwise direction. Whereas in this case, whenever the current is X mark indicates the current carrying conductor, and current is into the plane of the board. Current is into the plane of the board. So the sign convention, right hand rule, when you hold the current carrying conductor in your right hand such that thumb indicating the direction of current, that means current is inward, the magnetic field around it is in clockwise direction. Okay, magnetic field lines are clockwise direction, and they are the circular loops. Magnetic field, compared to electric field or circular path, electric field lines are not closed loops, whereas magnetic field lines are closed loops. Okay, so in case of straight conductor, the magnetic field lines are circular in path, and in case of electric field, we cannot say they are circular or they are not closed loop. It is only one sided, plus charge to minus charge, or plus to infinity, or infinity to minus negative charge. But here they form closed loops. This is the distinguishing property of the electric field and magnetic field lines. Electric field lines and magnetic field lines. These magnetic field lines form closed loop, whereas electric field lines do not form closed loop. Okay, so this is what the experiment conducted by Oersted, and he conducted another experiment keeping iron filings on a cardboard and made a small hole at the center of the cardboard and sprinkled some iron filing on the cardboard, randomly distributed. Then he passed a straight conductor carrying current perpendicular to the cardboard and connected to a battery. Okay, then whenever current is flowing through this conductor like this, okay, current is flowing through the conductor, and on the perpendicular plane there is iron filings, tiny piece of iron. Okay, in the blacksmith we can find that iron filings. Okay, whenever they do the iron work, so there will be some powder like object, so that is used here. So that iron filings, okay, when are spread on the cardboard. Now gently tapping this cardboard like this, what happened is the iron filings formed circular loops around the current carrying conductor, with the current carrying conductor at the center. That means this iron filings, the property of iron, it is a ferromagnetic material. It gets influenced by the magnetic field. Suppose if you take a magnet and if you touch the iron filings will hold that magnet. Means ferromagnetic materials are attracted by the magnet. In detail about this properties of ferromagnetic materials, we are going to study in the chapter number 5, that is magnetism and matter. Now here the iron filings what were present on the cardboard were sprinkled themselves, and they formed the loops, circular loops surrounding to the current carrying conductor, with the current carrying conductor at the center. So this shows that This shows that there is something, and this closed loops are because of the magnetic field or magnetic field lines. They are the magnetic field lines. Magnetic field lines or electric field lines, they are not physically present. We are drawing the lines, imaginary lines, to represent the magnetic field. What physically present is some field. Some field is there. We have to represent the field. So that's why we have to show some line or diagram you have to show. So everything we cannot imagine. So for imagination, to understand the magnetic field and electric field and show the presence of field, we are drawing the line, sometimes straight line, all that, to represent the field. Physically the line is not present, it is only the field. There is something around the magnet or the current carrying conductor, that so that it can interact with the another magnetic material, like it can be like it can attract or repel the magnet, or similar another conductor. If you take and pass the current, it will if the currents are in same direction, that will attract. If the currents are in opposite direction, that will repel. That means how these two current carrying conductors interact each other, it is based on the force. Which force? Magnetic force. One conductor produces force on the other conductor, so that means they interact by means of magnetic field produced by each of them, and they interact each other. So they will exert force between them. That's why there will be attraction or repulsion. So this is the basic idea given by Christian Ørsted. He conducted all this experiment, and he found that this kind of pattern observed on the cardboard. So this is I place this cardboard is perpendicular to the board like this. So cross section view, it looks like this. When I turn this and show, so that there will be circular paths shown by the iron filings. So that indicates the iron filings form circular loop because of the magnetic field which is produced by the current carrying conductor. So finally he concluded that the current carrying conductor or the moving charge produce magnetic field in the surrounding space. This is the conclusion given by the Christian Ørsted. Greater the current, greater field is produced, and the needle showed greater deflection. And when the needle is brought closer to the conductor, then it shows greater deflection, means more deflection, because the needle at the same time it is affected by the magnetic field of earth also. Magnetic field of earth also influencing this needle. So but it has to dominated by this current, means there will be considerable amount of current in the wire, or it should be nearly very near to the conductor. If it is far away, it is influenced by the magnetic field of earth alone, not by this conductor. Because magnetic field of earth, even though it is weaker, but it is spread all over the earth, whereas this field is when the conductor is when the needle is very near to the conductor, then that field will affect this needle. When it is far away, this current is negligible, and that field is negligible by this current. So that is the idea. When the needle is brought near the conductor, that shows more deflection. When the needle is far away, it is showing less deflection due to this current carrying conductor. And also when the current direction reversed, the direction of the needle also reversed. So he traced along the circular path. So this needle was shown continuously. He put once he put the needle and marked the points. Next he put the needle and marked the points. So next time he brought here, and south was showing here, north here. And so continuously he kept on keeping the needle continuously. He has drawn that, and he found that it is circular path. So that is the actual path, and that path is the magnetic field line, and that is the magnetic field produced by the current which is flowing in the conductor perpendicular to the board. Here current is normal outward, here current is normal inward. So you have to use the right hand rule to find the direction. Say current outward, so field is anti-clockwise. Field lines are anti-clockwise. So north is shown by the shaded region here, and south is unshaded region, opposite. Okay, so this is north and this is south. This is north pole of the needle, and this is south. This is north and this is south. Likewise we write the north. So here it is reversed. Direction of current is reversed, though needle orientation also reversed. Okay, so that, and then next when the current strength is increased, the deflection in the needle increases. So these are all the facts studied by Christian Ørsted regarding magnetism. So the sign convention is the current coming out of the plane surface or any surface. Current normal outward is shown by the dot with a circle. Okay, this is the current or field coming out of the board. Okay, normal outward. It can be current also, it can be field also. Normal outward is shown like this. Okay, if I show like this dots, that means the field, if it is say I say magnetic field, so magnetic field is normal outward. If I say x like this, then I have to understand that the magnetic field is into the plane of board. X mark indicates into the plane of board. Here current is flowing into the plane of board. Here current is flowing out of the plane of board. So like that. So this dots or dots with circle represent the field or current normal, perpendicular and outward. And this also shows the field or current normal into the plane of the board. And current or field means both electric and magnetic field in a space or region. So that is about the experiment. And then we go to the next topic, that is okay, so the next topic is magnetic force on a charge. Magnetic force on a charge. So whenever a charge at rest, it experiences electric force. Whenever there is an electric field, that part you should read in a first chapter. Whenever a charge means it may be proton, it may be electron, or group of protons or group of electrons. Some amount of charge we express in coulomb. Whenever you place a charge in an electric field E, then it experiences a force QD, where Q is the charge, magnitude of charge also, or charge. So force experienced by the charge, it is electrostatic force. It is at rest also. Now whenever you make a charge move in the magnetic field. So when the charge particle, it may be a proton, it may be electron, alpha particle, or any charged particle moves in the magnetic field, it experiences force, that is magnetic force. In the magnetic field, a charge is made to move. So remember, when a charge is moving, it also produces magnetic field, and it is producing magnetic field and moving in another field. That another field is externally applied field. Externally applied field may be field produced by a magnet, or field produced by a coil, or field produced by a solenoid. But when this charge is flowing, it will produce field, and that field produced by that charge varies from near distance to far distance. As you go away from the charge, the field decreases. Like current carrying conductor, field is greater, very near to the conductor, and field strength is lesser and lesser when you go away from the conductor. So that idea you have to keep in mind. So here whenever a charge is moving, okay, so on a moving charge, there is magnetic force on a moving charge. Moving charge, that means a moving charge only experiences the magnetic force. A stationary charge will not experience any magnetic force. The moving charge experiences a force Fb. It is a vector. Force is a vector. Fb vector equal to Q times V cross V. So this is the expression for the magnetic force experienced by a charge Q. Okay, it may be a positive value of charge or negative value of charge. Then V cross V, where V is the velocity vector of that charge. Means with what velocity it is moving. So it has got both direction and magnitude. That's why the vector symbol I have shown. And there is a magnetic field direction. Okay, field direction is there, in which it is also vector quantity. So the force experienced by the charge moving with velocity V and magnetic field in a magnetic field B is given by this expression, where Q is the charge. That Q value can be positive or negative. If it is proton, I have to substitute E. If it is electron moving with certain velocity, I have to substitute minus E. Okay, so there is a difference. Forces are different in direction whenever you take plus E and minus E. So that I will discuss next. Now, a charge is moving in a magnetic field, it experiences a force given by this, and this magnitude of this force Fb, I denote the magnetic force by Fb, not Fm. So Fb equal to Q and cross product. This one we can also write QVB, Q into magnitude of velocity into magnitude of magnetic field VB sin theta into n cap. Sin theta into n cap. This n cap is the unit vector which is perpendicular to V velocity V vector and magnetic field B vector, and it is found by right hand rule. Whenever it is cross product, we have to apply right hand rule. In simple ways I can say, if vector A like this and vector B like this. So we have to show from when we curl the finger from A to B, vector A to B, okay, A to B like this. The direction of A cross B is normal outward from the board. I show here like this. This is the direction of vector C, that is equal to A cross B. The direction of vector C is outward from A and B, I mean perpendicular to both A and B. Perpendicular means angle between C vector or A cross B and B is 90. Angle between A cross B and A is also 90. Okay, that means A and B are in the plane of line on the plane of board. Then the C vector is normal outward from the plane of board according to right angle. If you curl the finger from A to B vector, then the thumb indicates the direction of cross product A cross B. This is what you studied in first year system of particles. There some explanation regarding or about this cross product is given. Here the cross product, so this n cap direction of this A cross B is perpendicular to both A as well as B. So that is shown by this n cap unit vector. Unit vector gives the direction perpendicular to the both the vectors A and B, or it is in the direction of A cross B. So A cross B, this is the magnitude of this A cross B, and n cap is the unit vector which indicates the direction of A cross B. Okay, so magnitude of magnetic force is QEB sin theta. Now magnitude, if I write, it is QEB sin theta. Now we try to understand these facts. The magnetic force depends on what are the terms. It depends on the magnitude of charge. It depends on the velocity with which the charged particle is moving. It depends on the magnetic field in which it is moving. Magnitude of magnetic field means more magnetic field, more force it experiences, all directly affecting, and depends on the angle between the velocity vector and magnetic field. Here theta is the angle between in what direction charge is moving and with respect to the magnetic field. If V and B are perpendicular, field is like this, charge is moving this way. Field is like this, charge is moving like this, perpendicular. Angle between B vector and V vector is 90 degree. The charge experiences maximum magnetic force, because sin 90 degree we know that it is 1, maximum value of sin theta is 1. That happens when theta equal to 90 degree. Theta equal to 90 degree. In physics what I can say, velocity vector of the charge, in what direction it is moving, and magnetic field present in the space, both are perpendicular. Then sin 90 degree, 1 theta is the angle between V vector and B vector, both are perpendicular. Force experienced by the charge is maximum. Then that means the magnetic force depends on charge, depends on velocity, depends on magnetic field, and depends on the angle theta between the velocity vector and magnetic field vector. Now the force can be zero in some situation. When can be the force on this charge be zero? So it is possible when the particle is uncharged. Q equal to 0 means uncharged particle. Can you understand or can you recall which are all uncharged particles? Photon is uncharged, neutron is uncharged. Okay, so photon, neutron, etc., if they are made to move in the magnetic field, they do not experience any force. Whereas proton, positron, electron, alpha particle, these are all charged particles, they experience the force. But a photon, light particle we call photon, or this one, neutron, which is there in the nucleus, that neutron is also uncharged particle. So in case of uncharged particle, magnetic force on that particle is zero. Okay, so then velocity is zero if the particle is stationary in the magnetic field. Velocity zero means particle is not moving, it is stationary at rest. Then also magnetic force on the particle is zero. Then magnetic field B, no field is applied, charge is moving. Then also there is no magnetic force on the charge. Then theta 0 or theta 180 degree also I can take. Then also the value, okay, stationary, right? I will complete writing all this. Stationary NaRy, okay, not NeRy. NeRy means stationary materials, book, pen, pencil, all that you get in the shop. that is stationary. Okay, there is a difference in the terms. Stationary like this. Okay, stationary or rest. Particle stationary rest, that is velocity 0, force is 0. Okay, if, okay, right. Then another condition, if there is no magnetic field in the region, field is 0, and if theta 0 degree or theta 180 degree also, the magnetic force on the charge is 0. Theta 0 degree or theta 180 degree means what? There is a magnetic field like this. Okay, this field lies say uniform field only. If a charge moving along the direction of the field, or a charge moving, okay, this is the charge I say, along the direction of the field, theta is how much? They are parallel, V vector and B vector are parallel, means theta is 0 degree. Or I can take, if the field is like this, okay, if the charge is moving this way, okay, velocity vector for the charge is this way and the field is right side, charge is moving towards the left, then the angle between Q and B is 180 degree. Vectorially I can say angle is, one is this way, charge is moving towards left, whereas the field applied towards right. Theta equal to 180 degree. In that case, what is the force on the charge? 0. So a charge experiences, or a particle experiences no magnetic force if it is uncharged particle, if it is stationary, if there is no magnetic field applied, or after satisfying, it is a charged particle, it is a moving particle and there is magnetic field, but still force can be 0 if it is moving parallel to the field or it is moving opposite to the field. So in that cases, the force experienced by the charge is 0. Now force experienced by negative charge is quite opposite to that experienced by positive charge. That means if there is a positive charge flowing like this, it experiences force this way. There is magnetic field. Now instead of there is a positive charge, a proton moving like this, force experiences upward if I take. And if there is an electron flowing this way, there is magnetic field in the region. The force is opposite. That means force experienced an electron will be downward. That means a negative charge experiences a force in a direction opposite to that a positive charge experiences. If positive charge experiences upward direction force or force in upward direction, the same field, same direction of motion of the particle but negative charge like electron, it will experience the force opposite to the direction of the force experienced by the positive charge. So that are the conclusions. Then force vanishes. They may ask force vanishes, disappears. This case only. Okay, direction of force is determined by the right hand rule. Right hand rule means it is used to find the direction of the cross product. Right hand rule. So it is the direction from velocity to magnetic field. Okay. If you want the diagram, let me show the diagram. Suppose there is a magnetic field. Here I will take magnetic field like this. So I hope you understood. This magnetic field is normal into the board. Okay, X mark means normal into the board. Okay, normal into the board. Then I will take a particle going like this. Okay, charged particle. I will take positive charged particle going like this. So what is the direction of the force experienced by this charge? Field is normal into the board. Charged particle moving to the right, I will take positive charge. Okay, positive charge. Then what is the direction of the force and how to find the direction of the force using this expression? Velocity is right side. So first finger I will take right side. Then magnetic field. The second vector is magnetic field. Magnetic field is into the board. See, just look here. First vector V towards right, second vector magnetic field into the board, third vector that is cross product is shown by middle finger, it is upward. So this charge experiences a force which is acting upward if it is a positive charge. If it is a negative charge, okay, upward means perpendicular upward, like this here. Charge is moving to the right, field is applied into the board. Force experienced by the charge is upward. That means it will not move in the straight line. Instead it will show deflection like this. The dotted line will show the trajectory after some distance it travels. It will goes along the dotted line. It will not go straight. At this point the direction of velocity is like this. At this point, after some distance the direction of velocity will be like this. That means if the charged particle is moving perpendicular to the magnetic field, it will